Hello everyone, my name is John MacDonald. I'm a lecturer at the University of Glasgow in the School of Geographical and Earth Sciences. In this short video, I'd like to talk about how we can mineralise atmospheric CO2 to help us meet our net zero targets. So, of course, we need to work very hard to try and keep global warming below 1.5 degrees Celsius, figure you hear quoted a lot in the news. And, you know, as we all know, there are many ways of doing this. Particularly, our focus is on reducing our CO2 emissions. So through things, what we might call traditional mitigation technologies. So that would be things like transitioning from fossil fuels to renewable energy sources. Now, as we sort of head towards, say, the end of the century, this kind of transition, so reducing our CO2 emissions, for example, from transitioning to renewable energy, will help us reduce the global CO2 emissions that we emit every year. However, there is another smaller but still significant approach that we can take to reducing the amount of CO2 in the atmosphere and therefore attempting to keep global warming below 1.5 degrees Celsius. And that is removing that carbon dioxide, from the atmosphere. Now, we could do this either as we are producing it, so say in a fossil fuel fired power station, for example, or we can try and draw down CO2 gas that's already in the atmosphere. And this latter approach that I'm interested in my research, and the different kind of materials that we can use to draw that CO2 out of the atmosphere. Now, in particular, I'm interested in a material called slag. It's a byproduct from the steelmaking industry. It looks a bit like a rock, kind of greyish colour, as you can see in the photograph here. A bit more close up, because it's quite porous, it's got a high surface area, and it's quite reactive. It's chemically reactive, and it will react with atmospheric CO2. So in this chemical reaction that we can see down the bottom, slag is made of calcium, silicon, and oxygen, calcium silicates, and that can then react with our atmospheric CO2. Now, the products of that reaction, we've got sort of byproducts, just silicon oxide, inert, but then we've got this other thing that's forming, which is our mineralized CO2. So the CO2 gas is reacted with the calcium in the slag to create this new mineral called calcite, calcium carbonate. So this is quite important because the CO2 is going from a gas phase where it's existing in the atmosphere, and as a gas it can contribute to that global warming. Whereas through this chemical reaction, it then transitions into becoming a solid material. So of course, then it's no longer in gas form in the atmosphere where it can contribute to global warming. So in my research, I look at the microscale aspects of this chemical reaction, so the CO2 mineralization with materials such as steel slag. So I use microscopy and chemical analysis to really try and better understand this chemical reaction and give us that kind of fundamental understanding that we need to then think about sort of optimizing this process of mineralizing atmospheric CO2. So if we can understand the fundamentals of the process, we can then optimize it to try and make sure that we can use this material, this industrial byproduct slag, to remove as much CO2 from the atmosphere as we possibly can. So on this slide, we can see a microscope image in the left panel here. And this is just kind of showing the reaction textures of that chemical reaction on the previous slide. As we view down the microscope, an electron microscope in this case, after that chemical reaction has at least partially occurred. So what we can see is these kind of pale grey zones, for example, down here in the bottom left of the image, And these are fresh areas of slag, so slag that hasn't actually reacted with the CO2 yet. The mineralized CO2, so the product of the reaction, is this kind of uniform gray color, and that's forming a sort of lining around these pore spaces in the slag. And then we've got this kind of buffer zone in between those two, this sort of darker but sort of speckly colouring here between the yellow and red dashed lines. And that's a zone on the sort of edge of the slag where the calcium has been leached out and gone into forming this calcite, this reaction that we saw in the previous slide for mineralizing the CO2. I also use other analytical techniques, things like micro CT scanning, so a bit like a hospital CT scanner, but for looking at rocks and other solid materials such as that. What we can see in this image on the right, this is a 2D snapshot of a 3D reconstruction of a cube of slag, which is the sort of pink color. That's the slag material, with some mineralized CO2 formed on it, so our new mineral calcite, and that's in the green color here. And what's significant about this is that we can see that there is sort of different behavior going on here in terms of how this chemical reaction is forming. So we can see that some pores here with this sort of circular shape have a sort of thin lining of the calcite forming in them. Some are getting pretty much completely filled, and then others have sort of different shapes of calcite crystals growing in them. So we can see in this one here, perhaps some kind of needle shapes. So that's the kind of microstructural or microchemical aspects of this chemical reaction that I'm particularly interested in. So what we can sort of show from this kind of research is that mineralizing CO2 with materials such as slag can indeed help contribute to our net zero targets, but further research is needed on this process to really think about how we can optimize it to really maximize the amount of CO2 that we can draw out of the atmosphere in this way. So thanks very much for watching the video. If you're just to find out more, please don't hesitate to get in touch with me either on email or on social media. Thanks very much.